Our final section in this chapter is going to be about variation. So we're going to go through two things. We're going to first start out with talking about direct variation, and then after we get familiarized with that, we'll talk about other types of variation. So first and foremost, the reason that this section kind of pops up in the same unit is because variation is very similar to proportional, at least in the direct case. So what we mean by saying y varies directly as x, there basically is a nice relationship between the two. So one is going to be a constant multiple of the other. So if our input doubles, the output will double. If the input halves, the output halves. So basically what happens to one happens to the other. So what we say is that y varies directly as x if there exists a real number k so that our variable y is equal to some constant times x. This number k is called our constant of variation, and really this is just a linear equation. It's what we learned about earlier in the semester. But what we can say is that y is directly proportional to x. So in this sense, if our x doubles, the y is going to double. If x triples, y is going to triple. So there's that direct relationship between the two. So let's start with an example. Suppose you work 43 hours in a single week and you end up getting paid $795.50. We're going to answer two things, and the very first question is going to be how much do we earn for each hour that we work? So thinking of this just in the real world sense, if you take your paycheck and you get your total amount and you divide it by the number of hours, it tells you how much you made in a single hour. So we're going to take our total amount of $795.50 and we're going to divide it by the amount of hours we worked. So if you take the $795.50, divide it by 43, what you're going to end up finding is that this is $18.50. So we're earning $18.50 per hour that we work. Okay? So all this really is a direct variation equation. If you want to figure out what your paycheck is for the week, assuming you don't make extra for overtime or anything like that, you're going to take the number of hours you work and you're going to times it by a rate. So from one week to another, if you double the amount of hours, you're going to double your paycheck. If you work half the amount of hours, your paycheck's going to be cut in half. So for this next one, we want to write an equation of what our pay is, P, after we work H hours. So our pay is going to equal our hourly rate multiplied by the number of hours we worked. Okay, so that is exactly what you do at whatever job you've had in the past, or if you haven't, that's how you figure out your pay for future hours. So they're telling us our pay is represented by the variable P, our hourly rate is $18.50, and the number of hours worked is also a variable that we're calling H. So this is exactly the form we have for direct variation. We have a constant times our input value. So what we can say is P varies directly as H. Okay. Let's try another example. We're told the weight of an object on Earth is directly proportional to the weight of an object on the moon. A 200-pound astronaut weighs 32 pounds on the moon. So before we jump into setting up equations and trying to solve a problem, just thinking about this. You on Earth weigh a certain amount because we have a certain amount of gravity. If you go to the moon, you're going to weigh a lot less because the gravity isn't as intense there. And what happens is, regardless of the person, the object, whatever it is, you're going to weigh some proportion of what you do on the moon than you do at Earth. So basically, I'm taking my weight and I'm going to multiply it by some fraction to be able to figure out what my weight on the moon is. And that fraction is going to be the same for any object. So what we want to do first is we're going to let X represent the weight of the object on Earth. Y is going to be the weight of the object on the moon. And since we have this direct variation relationship, we want to come up with an equation that represents this scenario. So what they tell us is our weight on the moon is directly proportional to our weight on Earth. So X is our weight on Earth, Y is our weight on the moon, And remember, this K is just some constant, but we just don't know it yet. So K is an unknown constant. But since we do have some pieces of information about one weight of a person on Earth and the moon, we can use that to figure out what this constant is. So my constant is unknown, but I know my weight on Earth for the astronaut is 200 pounds, and his weight on the moon is going to be 32. So I can fill in those two missing pieces, and then I can solve this equation for K. So I go ahead and I divide both sides by 200 to make those cancel out, and this gives us 32 over 200 is our value of K, and if you plug that into your calculator, that would be 0.16. So what we have in our relationship is our weight on the moon, Y, is equal to 0.16 times our weight in Earth. So if you think about this, 0.16 is also the same as 16%. You take your weight, you'll weigh 16% of that on the moon. Okay? And now that we actually have this equation to represent what's going on, for the second part we want to figure out is what would a 50-pound dog weigh on the moon. So if they weigh 50 pounds currently, we're going to times that by 0.16 to get our value of Y. And if you go ahead and multiply these two, you would see it would be 8. And remember, Y is what the weight is on the moon, so the dog would weigh 8 pounds on the moon. Okay. Now from here, we're going to just talk about the other types of variations, and then we'll actually do quite a few examples. So one thing that could happen is you don't just have to vary as x, you could vary as x to a power. So it could be like the square of x, x to the third, x to the fourth, something like that. But you're going to have the same kind of equation when you have y varies directly as a power. You have a constant, and then it's going to be time x to whatever power is given to you. So the same kind of thing will happen as x is going to increase, y is going to increase as well. So there's still that direct connection in that they're doing the same thing. If x decreases, y will also have to decrease. But it's just not as clean cut of a connection if one doubles, the other doubles. You can't say that anymore, unfortunately. The other type of variation is inverse. And so if you think of the word inverse, it's kind of like the opposite. Inverse usually means it's something in the denominator. So there's an opposite correlation between those two variables. So essentially the way you can think of this, as one increases, the other is going to decrease instead, or vice versa. So we can have the same kind of thing. We can have varies inversely, and we can have varies to a certain power. And the only difference in this case, instead of taking K and timesing it by the variable, inversely means we're taking the constant of variation and dividing it by the variable. And then when it's a power, it's the same thing. You're going to take the constant divided by the variable to whatever power they give you. So the best kind of real life example you can think of, if you've ever had to order t-shirts from a company, or if you try to order something in bulk, the more you order, the cheaper it is per item for you. Because if I'm ordering one shirt that's got a highly detailed design on it, it costs the company a lot of money to fork over the material to get that. But now if I want to make 10,000 of that shirt, it's going to be a lot cheaper because there's not that initial setup anymore for just that singular item. So the more I order, the cheaper the price is. So that's exactly what we're going to do in this problem. We're told the cost of producing a shirt varies inversely as the number of shirts produced. And then we're told if 10,000 shirts are produced, the cost is $2 a shirt. What we want to do from there is we want to figure out what is the cost per shirt when we're going to make 25,000 of them. So we have quite a few things that are varying in here. So I'm going to go ahead and I'm going to set up some equations for my unknowns. My number of shirts is going to change. The cost per shirt is going to change. And because does tell us it varies inversely, we do have our constant of variation, which is still currently unknown. Constant of variation, we're always going to use K for. For the other two, you can pick whatever variables you want. For the cost per shirt, I like C, makes sense. Number of shirts, you can use an S if you want, but personally, I think the S is kind of difficult because it looks like a 5 a lot of times. So I'm going to say it's a number. Let's use N. Okay. And now because we have this inverse relationship, our cost varies inversely to the number of shirts. So the cost is by itself, and inverse means it's a constant of variation divided by the other unknown. So what we want to do is we want to figure out what does this K have to be in order to be able to answer my N question. And that's where we're going to go ahead and we're going to use this piece of information. If 10,000 shirts are made, the cost is $2 per shirt. So ultimately, when the number of shirts is 10,000, the cost is $2 per shirt. So what we can do is we can plug both of those pieces into our equation setup and solve for K. So our C is 2. We don't know K, but then the number of shirts is 10,000. And then solving this equation, we go ahead and multiply by 10,000 on both sides. And so really that gives us 20,000 is equal to K. So I use that first piece of information to find my value of K. And so now I have the full equation. My cost is 20,000 divided by the number of shirts. Okay. And now that we've got our setup, we can actually go ahead and answer this next part. So we want, what is the cost per shirt to produce 25,000 shirts? So our goal now is what does C equal when the number of shirts is 25,000? So all we do is plug that into our equation. C is 20,000 divided by 25,000. And if you go ahead and plug that into your calculator, you will get 0.8. So for 10,000 shirts, it costs $2 a shirt. For 25,000 shirts, it costs 80 cents per shirt. Okay. And that makes sense. I produced more, so my cost is less. Now for these last ones, I really just have 4 more examples, and they're going to all be similar. Really going to follow the same approach as this last problem. You always want to set up your equation with that unknown constant of variation. You're going to be given a piece of information that lets you find the value of K. Once you then have your full variation equation, you can then use that to solve for that last unknown piece. So for this first one, we're told C varies directly with the square of B. So I'm going to start just by utilizing this. C varies directly. So that means I'm going to take my constant and I'm going to times it by something. And it says the square of B. So it varies directly with B squared. Okay. So this is my setup for the variation equation. And I need to figure out what this unknown K is. And this is where we're going to use the next piece. So C varies directly with the square of B. And then we're also told C equals 4 when B equals 3. So this allows us to find K. So C is equal to 4 when B is equal to 3. So I plug those two pieces in. So this is 4 is equal to 9K. Then I go ahead and divide both sides by 9. Those cancel each other out. And we get our value of K is 4/9. So the equation that represents this scenario is our C is equal to 4 over 9 B squared. So now that we have the setup, the equation or the question asks us to find what does C equal when B equals 2. So we can go ahead and figure out what does C equal when B is 2. So we just plug that in for B. So we get 4 over 9 times 2 squared, which is 4 over 9 times 4, which is 16 over 9. So this is our value of C that we are searching for. Okay. So again, really every single problem is going to follow the same kind of approach. You set up the equation, you find your value of K using the piece of information. Now that you have your full equation, go ahead and find that last missing piece. So this next one, now we have an inverse variation problem. Z varies inversely as W. So to set that up, our Z is the constant divided by W. And then we are told Z equals 10 when W equals 0.5. So we're going to use that to find the value of K. So Z is equal to 10 when W is 0.5. And now we go ahead and bring the 0.5 over by multiplying by it, which means we do that to the other side as well. So if you take 10 and times it by 0.5, you get K is equal to 5. So now our actual equation is the variable Z is equal to 5 over W. So we've used all of these so far. Now we can answer this final question. We want to find what does Z equal when W equals 8. So plugging that in, Z is equal to 5 over 8. And then really you could leave it here. This does have a nice decimal, so you could actually write that out. Our Z value is equal to 0.625. Okay. So again, exact same approach as the last one, just a slightly different setup at the beginning. For this next one, X varies directly as Y. X equals 9 when Y equals 3. We want to figure out what does X equal when Y equals 12. Now, a big question we often get is, does it really matter what order you put this in? And the answer is no. So you could put Y equals K times X, varies directly, so that doesn't matter. Or you can put X equals K times Y. You'll just end up with a slightly different K value, but that's okay. You'll still get the same thing. What I would recommend though is, because it asks us to find X, we're going to use this format instead. And really kind of looking at this, it says X varies directly as Y. So this means your input's going to be Y, your output is going to be X. Again, you could use this first one and it will still lead you to the same answer, but it's just you're going to have to do more work to get there. So X varies directly as Y, so we set it up in this way. We now know to use this particular point to find the value of K. X equals 9 when Y equals 3. So we plug those values in to get 9 is equal to K times 3. And then we divide by 3 to get K on its own, and 9 over 3 happens to be 3. So K is equal to 3. So plugging that back in, our X is equal to 3Y. And our real question is, we want to find what does X equal when Y equals 12. So we just go ahead and plug that back in for Y, which tells us X is equal to 3 times 12, which is 36. So this is what X must equal when Y equals 12. So I just got one more. Now we have an inverse problem again, but it's inversely as b squared. So I need to set this up. Because it's inverse, that tells us it's k divided by a number. And again, it makes no difference really where you put a and b squared, but we are searching for a in the end. So I would say write a is equal to k over b squared. Now we go ahead and we use this point that a equals 48 when b equals 4. So we replace a by 48 and we replace b by 4. And unfortunately, these are going to be some not so nice numbers. We have 48 and then 4 squared is 16. To get rid of the 16, we multiply it to both sides. So those cancel. 16 times 48 gives us a pretty large number of 768. And so that is our constant of variation. So going back to our starting equation, we now know a is equal to 768 divided by b squared. So we are almost done. What we need to do is we need to find the value of a when b is equal to 7. So we go ahead and just plug that in. A is equal to 768 over b squared. And 7 squared is going to be 49. And unfortunately, that doesn't simplify, so we just have to leave that as is. Based on this problem, this is what a must equal when b equals 7. Okay. So that is it for this last unit, or second to last unit. We have one more after this, and then we will be done for the semester.